Okay, in today's day and age, with the proliferation of digital devices, we've kind of lost the questioning how a computer, which is really just a larger version of a calculator, can add numbers, especially when we get to negative numbers. And so what I'm going to do today is I'm going to show you what we call 2's complement, which is the method that a computer or a calculator or any digital device uses to do a subtraction operation. And then the next time out, what we'll do is we'll actually build what we call binary adders. And that's one, so think about it, I just want to go through binary addition first. If I were to add a number, let's say 0, 1, 0 and 0, 1, 1. I'm going to add two 3-bit numbers up. So I'm going to put those together, and it is straight up addition. So I'm going to 0 plus 1 is 1. 1 plus 1 is 0, but when I need a carry, it's just like doing decimal addition. So I'm going to carry one bit to that third place right there. And 1 plus 0 gives me 1. So 0, 1, 0, which we know as decimal number 2, and 0, 1, 1, which we know as the decimal number 3, if we add those two up, we get the decimal number 5, and that actually turns out to be 1, 0, 1. 4's place, 2's place, 1's place. So I have 4 plus 1 would give me 5. And that's actually that's the math of it. So that's what we're going to do next time, is we're going to build circuits that it's no surprise, or should be no surprise, that it's a logic expression to come to that. If I just get down to it, I can come up with a logic expression, because there's a one-to-one mapping that says if I take this number and I add it to this number, I'm always going to get this number. They're functions, if we go back to our algebra thing. So what we're going to do is we're going to build an adder for this thing and deal with that, and then we're going to build another adder that's going to deal with the carry bit. Okay, so we'll deal with two different circuits there that do that. But that's for later. Before we can do that, one of the questions that would now be coming to mind is, how does a computer deal with negative numbers? Because everything gets turned into this random string of 1s and 0s, and I do mean everything. If you look at the actual raw data file for a picture on your computer, you're going to see nothing but a string of 1s and 0s. If you get it down to binary numbers, you probably would actually see it more as hexadecimal numbers. But we're going to do that. In order to understand the 2's complement system, we want to start by looking at what I'm going to call the 10's complement. So imagine if I had a number system. I've got a 2-digit number system like an odometer from perhaps a bicycle. And the thing is that if I take that bicycle and I start at 0 and I start riding out 1 or 2 miles and I go up this way, then I know that I've gone plus 2 miles. And so most of the bicycles being more simplistic and people don't care quite as much, if I were to go this way and kind of wrap around the end of my table and come back to the top, that would be negative 1 miles. If I went from 0 to 99, I actually went backwards 1 mile. And that would be negative 2 miles. And so on and so forth. So what we actually want to do is we want to define a middle point, which in this case is 50. So we're going to define the point of 50 as being the break between positive and negative. So 50, for the sake of argument for now, we're going to say would be positive 50 miles, and 51 would be negative 49 miles. And if you kind of look at it this way, one of the ways that I like doing this is rearranging my number system so that I now have the 50 here. And above there in negative numbers, for whatever reason I've put in green, is going to be 51, 52, and so forth up to 99. And that would be negative 49, negative 48, up to negative 1. And in the positive numbers would be numbers below there, so they'd be 49, which actually is positive 49, 48, which is positive 48, and so forth down till we get to 0, 1, which is positive 0, 1. And what this looks like, if you think about it, is my actual value, if I think about absolute value, is how far away my number is from 0. For 99, is actually 1 spot away from 0, and I can even do 0, which is neutral. Okay, that's what really should have really been in blue. 0 is actually 0, and it's neither positive nor negative, but 1 is 1 away from 0 in a positive direction. 2 is 2 away from 0 in a positive direction. 99 is negative 1 away from 0 in a negative direction, going backwards. And so is, in case 51, is actually 49 away from 0 in a negative direction. And that's the basis for my 10's complement number system. And so if I look at it that way, and that's kind of what I would have over here. So then let's look at how to complement a number. And the steps I've got written down here for. And first of all is you only complement the number if it's negative. If I'm trying to get a positive number, the 2's complement of a positive number is just that number itself. And you'll kind of see that in just a minute. So let's take the number, for example, negative 623, and we want to write that as a 10's complement this time. The steps are, if to complement it, you're going to take 9, which is the biggest number, biggest digit that I have in the base 10 system, and subtract each digit individually. So I'm going to complement each of the digits separately, and then I'm going to add 1 to the result of that. And so for negative 623, the complement of 6 is 3, which is 9 minus 6. The complement of 7, the complement of 2, rather, is 7, and the complement of 3 is 6. So I've complemented each of the individual digits, and now step 2 is I'm going to add 1 to that, and my 2's complement is 377. But the problem with this is that actually, in order to do this, I actually need a number system that's capable of handling the number 623 as either positive or negative. And I can't do that with this system. I've divided it. So what I really missed here was I needed to have an additional digit in front, which is going to be a 0 in the case of the original 623. And when I complement it, I'm going to get a 9 there, because 9 minus 0 gives me 9. And the actual 2's complement for this, which is actually required 4 digits, is 9377. And the fact that I had a number which I could have had up to 9,999, sorry, the fact that this number is greater than, that's greater than 5,000 is what tells me that that's really a negative number. And if you look at that, if I look at kind of where that is and try to place that relative to the maximum number I could have had, if I do 10,000 minus this 9377, then I'm going to get a 3 there. And that's going to give me a 9, so I'm going to get a 2 there. Because I had to borrow, I had to borrow from over here to get a 10. So that's a 9 now minus 2, and that's a 9 minus 3 is 6. And that's a 9 minus 9 is a 0. And what that tells me, I'm looking at here, that this number, 9377, is actually, sorry I went off the page there a bit, 9377 is actually 623 away from 10,000, which is kind of what we were looking at on the other side of this. We were looking at the fact that we were dealing with numbers, how far away they were from 0. So your negative numbers kind of run backwards. All right? So then the next thing is I want to do is move from 10's complement to 2's complement. And 2's complement's a very similar system. Sorry, I got a lot of stuff here. 2's complement's going to be a very similar system in that I need to break my number system in half. It's a little more convenient now because in 2's complement, every time I add a bit, I double the number of numbers I have. So if I had 2 bits, I can count up to 3. Really, I can count 4 different total numbers. If I add a 3rd bit, I can count up to 8 numbers. If I add a 4th bit, I can count up to 16. So the first thing that happens is in 2's complement, my first bit is always going to be my sign bit. It's a little easier this way than it is in 10's complement. But I'm going to do the same thing. I'm going to start with 0, 0, 0 as my neutral number. So that really does represent 0. And if I look at what the complement of these numbers are, it is. if I work my way down here, I'm counting up. So I'm going to go 0, 0, 1. And so I'm going to go into a positive area. I'll make these green. That really is 1. 0, 1, 0 is 2. And then 3 and so forth. Until I come to, even though I have a 5-bit number, my first bit is the sign. So the 0 tells me it's a positive, and I have 1, 1, 1, 1, which is a positive number 15. If I go upwards from there and count here, so I'm going to have 0, 0, 0, 1 with the 1 in front. That is 15 away from my maximum number. And I can count my way upwards here. This is going to be negative 3. This is going to be negative 2. And this is going to turn out to be negative 1 because it's 1 away from 0, 2 away from 0. If I think about my number system kind of wrapping around and being one big circle, and 3 away from 0. The steps are the same. If I want to 2's complement a number, I'm going to do it the same way that I did with 10's complement. The big difference is now my maximum character, I can't say digit because that's a decimal thing, my maximum character is actually 1 and not 9. So again, 38 is going to be just the way it is represented in binary. So then I would need 5 bits to represent the number 38 because it's going to have to include 32. So 38 would be 32. The next bit would be the 16's place. If I subtract 32 from 38, I get 6. There's no 16's in it. There are no 8's in it, but there is a 4, and then there is a 2, and then there are no 1's. So I just said that wrong. 5 bits would give you, the biggest number you could get would be 31. I needed 6 bits to do that. In order to make this a 2's complement, I'm going to have to include one additional bit, which would give me the sign. And so my additional bit here is going to be the 0. And that's the 2's complement number for a positive 38. If I want to do negative 38, I'm going to have to go through the complement process. And I'm going to take each of the bits, so this one is not going to be the final answer when I write it down here. And I start with the same thing I had before. I'm going to have a 0, 1, 0, 0, 1, 1, 0. And I'm going to subtract, or rather I'm going to complement each number, which really becomes easy in binary because I've only got a choice of a 1 or 0, so this becomes 1, 0, 1, 1, 0, 0, 1. If it's a 0, make it a 1. If it's a 1, make it a 0. And then I'm going to add 1 at the end. And my final result, my final answer is here's going to be 1 and 1 is 0. I carried 1 and get it there. And from that point on, everything stays the same. So this is my 2's complement version of negative 38. The other thing is there's another way to do this. It's a shortcut. That's kind of the mathematical way and the purest way of doing that. But if you think about for a moment this number, my original number 38, and think that there's a bird flying through it, that they could pass through the openings and the zeros. They could pass through the middle of those okay. But the first time they hit a 1, imagine it's like a wall. And the first wall stands, but it's going to shake and it's going to push all of the other walls over behind it, and then that's going to change everything from that point forward. So if I have my little birdie flying through here, if I have my little birdie flying through the original number 38, it goes through the 0, but it hits the 1 right there. And so the 0 remained, the 1 remains, but after that, the next one became a 0. Those 2 zeros converted to 1s. The 1 changed to 0, and that last 0 changed to a 1. And that's it. Now this first bit, again, has nothing to do with the absolute value of the number. It has to do with, is that number positive or is that number negative? So this is the equivalent of negative 38 in 2's complement, and this up here is the equivalent of positive 38 in 2's complement. So now let's look at how we use that in a mathematical sense in trying to add the numbers. So first of all, I'm going to take negative 9 and negative 5, and I'm going to add those up. And first step is I need to represent the numbers in 2's complement. So negative 9, actually the first step is I need to represent them in a binary number. And since they're negative, then I'm going to complement them. So 9 is 1, 0, 0, 1. And 5 is 1, 0, 1. The first thing is all of my numbers have to have the same number of bits. So that's going to be 0, 1, 0, 1. And the other thing is I need that sign bit out front, which initially it's going to be a 0. Okay, it's going to turn when I complement it. All right. And so that was writing them as a binary number. Because they are negative, I'm going to complement them. And that means I'm going to do I either change all of the bits over, which means that's going to be 1, 0, 1, 1, 0, plus 1 is going to give me 1, 0, 1, 1, 1. And this one is going to be a 1, 1, 0, 1, 0, plus 1 is 1, 1, 0, 1, 1 again. And now I'm going to add all of these numbers up, or all these bits up, rather, and come up with an answer. And when I do that, 1 and 1 are going to give me a 1 carry a 1. Excuse me, they'll give me 0 carry a 1, won't they? 1 and 1 are going to give me 0, but I got the carry, so now I've got a 1 up here. I'm going to get 1 and 1 and 0 again, so I'm going to get 0 carry a 1, 0 carry a 1. I'm going to get a 1 here, and I've also got another carry, so there's 1 out here, and I've hit my first problem, I believe. I had a 1, 2, 3, 4, 5-bit number, and now I have a 1, 2, 3, 4, 5, 6-bit number. When that happens, I just throw that extra bit out. You literally can throw it away. And if you think about a computer system, you've only got so many bits that you're keeping up with. The system won't even allow you to deal with an extra one in there somewhere, so it would get thrown out if we were dealing with it with computers. And because I look at this and say the first usable bit is 1, that means the number is going to be negative. That means I need to go back through the complement process. So this time I'm going to use the bird flying analogy. And if I have a bird that flies through here, they're going to go through the 0, and the first 0 from the right is going to stay. The first 1 is going to stay. But those next two numbers change. They're going to be a 1, 1, and then I'm going to get a 0. So my number here is 1, 1, 1, 0, which is going to be 8 plus 4 plus 2 plus 0, which is 14, and the fact that it was a 1 there at the beginning is going to mean that it was negative. So this is my clue that it's negative right there. And that's my 2's complement process, which negative 9 plus negative 5 will give me negative 14. So that's simply the 2's complement process. You can work on that. I'm working through these in class, and then as I said, next class we will actually build the adders that will take digital logic and create the circuit that will do the addition for you. But what we've essentially done here is made it where subtraction can be done with the same machinery, the same hardware, and the same logic circuit that we've done to do positive number addition.